What's going on, everybody? Happy New Year's Eve. I hope you're enjoying the end of the year 2020. Hopefully 2021 brings us a lot more fruition and a better experience than this past year did, though I'm glad we've all seen it through to the end together. Today we're going to take a look at something pretty cool, and the phrase, "this isn't rocket science," can be thrown out the window because that's exactly what we're looking at. It's a specific area of rocket science. So we're going to be looking at a theoretical calculation for the center of pressure of a rocket in flight through atmosphere. Specifically, we're going to take some assumptions on this problem to make the problem itself a little bit more simplistic, as calculating the center of pressure is an extremely tedious process that requires a vast knowledge of calculus, both integral and differential calculus, as well as a full understanding of type of physics known as fluid mechanics or fluid dynamics. Fluid mechanics and dynamics, this is an area that is still not completely understood by physicists today. And the most exact expressions we have to explain and model physics in fluid dynamics aren't complete. For instance, we don't know exactly how to model turbulent flow, so we can't predict an outcome from turbulent flow. With that in mind, we have to take a few assumptions to allow us to actually calculate something here. And it's still going to be a tedious process, but we're going to make it as simple as we can. So, the first assumption is that the angle of attack for the rocket in flight is near zero, so we're talking less than 10 degrees. The speed of the rocket is much less than the speed of sound, so in empirical units we're looking at a velocity that's less than 600 feet per second. That the airflow over the rocket in flight is smooth and doesn't change rapidly. This is talking about turbulent flow, so it's saying that we don't experience any actual turbulent flow. That compared to its length, the rocket is thin. And you can see on our diagram on the left side of our screen, our rocket for this example is thinner than it is long. Or sorry, yes, it is thinner than it is long. That the nose cone comes smoothly to a point. Again, you can see on our diagram, our nose cone is a literal cone, so it does come to a point like that. That the rocket is an axially symmetric rigid body. Essentially what this means is that from a central axis, the rocket can be looked at as a solid rigid body with no interchanging parts that are going to be different speeds or velocities in flight compared to other parts in the rocket, and that it's symmetric all the way around. In this case, it is. And lastly, any fins are thin, flat plates, and in this case, they are. So, essentially what you're doing to simplify this, because we know a rocket is a three-dimensional object, but we can look for the center of pressure in a two-dimensional world and generalize that so we can help find it even if it is three-dimension or higher dimensions. So to do so, we would essentially take a two-dimensional projection of the rocket itself. So you could literally take your rocket and draw out its shadow. The rocket's shadow is a two-dimensional projection of a three-dimensional object. So essentially we've done that here. On the left side of the screen you can see we've drawn a two-dimensional rocket. It has a nose cone, a body section that gets bigger, and it collapses back into the engine compartment where the fins are. We'll discuss in detail what all the specific values on there are shortly. But first and foremost, we need to look at the total normal force on the rocket to really figure out where the centers of pressure are for each part. That way we can calculate the total center of pressure for the combined components to create the entire rocket. The normal force is denoted generally as N, and you can see on the bottom left side of our screen we have this N equals C sub N alpha multiplied by 1/2 rho times V squared times alpha times A sub R. Now, what these values are depicting are N is the total normal air pressure force. So this is the total force provided to us, the normal force provided to us by the air pressure around the rocket. C sub N alpha is generally it's a dimensionless shape coefficient for the specific part. So for instance, we'll talk about it soon, but you can see on screen now the nose cone for that shape, a conical nose. It has a C sub N alpha of 2. And that's generally for all nose shapes. The force is going to be 2. Rho is the unit or the variable used for air density or fluid density. In this instance, it would be air density, so we would look at the density of the air in the atmosphere. That's generally 1.01 times 10 to the 5th pascals in atmosphere, if I'm not mistaken, at least close to sea level. V, of course, is the velocity of your rocket, so we're looking at a v squared, which would give you meters squared per second squared. Alpha is your angle of attack, and A sub r is the reference area indicating the size of your rocket. Generally, it'd be a cross-sectional area at the base of the nose. Okay, so if we begin to look here, we know we're going to have a lot of parts to the rocket, because rocket in this sense isn't just a solid tube. If it was a solid tube, the problem could get a little bit more simplistic, but I didn't want to make it an overly simple problem. Since this is a physics channel, we wanted to at least ramp it up and give a little fun mathematical exercise. All right, let me come in the screen here. So we're going to take a look at everything on the basic rocket I've laid out here, this two-dimensional projection. We're looking at things trying to find the centers of pressure, and how we're going to do that is by finding these coefficient values for each component and taking essentially a change in distance in between the actual centers of pressure and the distances from a given reference line. Reference line we're going to use for the rocket throughout the entire thing essentially is the very tip, the nose tip reference. You could also do a reference line at the very base of the rocket, so the lowest part, which in this case would be our fins. But in our case, we're going to take the nose tip as our reference line. So, starting on the left side here, we have reference lines coming down, and these portions that give us a circle with a dot in it, these are our C sub n alphas per each component. So for instance, here is the normal force for the nose, normal force for this conical portion, normal force for this conical portion, normal force for the fins. Then this is the normal force combined for the entire rocket. So the actual center of pressure here is combined at this point from all components. What these X's are denoting is the distance from that reference nose tip line to that specific center of pressure. So for instance, X sub F is the distance from this nose tip reference to the very root of the fin itself. Then delta XF is the difference in between the root of the fin, so the distance to the fin, and the centers of pressure for the fins. X bar sub F gives us the distance to that center of pressure. And these values will actually help us a lot in the future when we're actually trying to calculate this. So we have, going further in from everything, we have a distance to the center of pressure for the fins, distances to the centers of pressure for this conical bow tail, which is the end portion connecting off of our main body, the centers of pressure for this conical shoulder and the distances involved, and the centers of pressure for the nose and the distance involved there. This all culminates, like I said, in this total center of pressure for the rocket, and we have the X bar, which is the total distance to that particular center of pressure. So, moving on, we know we're going to have to find the particular values, component values for each component to be able to calculate the entire center of pressure for this rocket. If we start at the very top where our reference line begins, we can look at the nose. In general, the C7 alpha, which we're also going to denote specifically for each portion in parentheses with a subnotation of that component. In this instance, nose, so we're using N for nose. We also did a little color coordination, hopefully that helps out a bit as well. So in general, the C sub n alpha for the nose, which is the normal force on the nose, is identical for all shapes and has the same value. So we're going to have a value of 2 for this. The center of pressure location, though, varies per differing nose shape. So we could have various nose shapes, particularly like this one, we have a conical nose, which in a two-dimensional projection gives us a triangle, essentially. You could have a parabolic nose, which is more like a bullet, and it's a lot more rounded. So you can have a parabolic nose that would be like this. And there are other noses, of course, like the Mercury capsule. If I'm not mistaken, I believe it was something along the lines of this, which is a vastly different nose shape than a cone or even a parabolic. But for simplicity's sake, we keeping it as just the cone. So for this conical nose, x bar sub n, which is going to be the distance to our center of pressure for the nose, is going to be denoted as 2/3 L sub n, where L sub n is the entire length of the nose itself, from the reference tip to the base of the nose. So this is 2/3 L. Then moving on to the next portion, going down, we have this long conical body. Well, we'll discuss the conical bodies a little bit later when we get to the bigger one as well. For now, we're going to move on to the next piece under that, the conical shoulder itself, which we denote CS for conical shoulder. So you can see in the smaller diagram here, we have the body that's coming into the shoulder here, and then the bigger body coming out of that. So the calculation for this particular component's normal force is a little different. It's not going to be the same value per every shape, of course. This shape, of course, gives us a trapezoidal projection. So the calculation we're going to get here is the C sub n alpha, the normal force for the conical shoulder, is going to equal 2 multiplied by a series of diameter equations, essentially. So we have two diameters we're looking at. We're looking at the diameter of the top cylinder here and the diameter of the thicker cylinder beneath it. So the notation's a little wrong on here. Let me fix that. All right, so we have D1, D2, and then there's a D3. 3 cylinders on there, of course. Each of these Ds is a diameter value in whatever units, just making sure that you keep your units the same values, of course, keeping symmetry all the way through the equations. So for the conical shoulder, we have 2 diameters we're looking at. D1 being the smaller diameter at the top, and D2 being the larger diameter beneath it. So for our calculation for this normal force, we have 2 multiplied by the quantity of D2 over D squared minus D1 over D squared. D is the diameter at the base of the nose. So the base of our conical nose is where we get the diameter for D. So you would calculate these values and we'd get an actual number for this. Looking for the position or the location of the conical shoulder's center of pressure, we find x bar sub cs equals xcs plus delta xcs. So if we look at our diagram here, we see that delta xcs is measured from the top of the conical shoulder to where the force acts itself. So this is delta xcs here. It's measuring from the top of the conical shoulder to where the force, the normal force on the conical shoulder is acting. And xcs, no bar, xcs, is the distance from the nose tip reference to the top of that particular component. So in this instance, xcs is the top of the conical shoulder. So to find the actual distance, location to the actual pressure point, center of pressure for this conical shoulder, we need to add in that first length value plus the change in length value. That gives us a new expression. So we get the first distance, xcs, which would be some measurable distance that we know, plus L sub cs, which is the length of the conical component itself, divided by 3, multiplied by the value for 1 plus the quantity 1 minus d1 over d2, all divided by 1 minus d1 over d2 squared. Again, these d's are the diameters for the cylindrical pieces above and below the conical shoulder. These would be calculable. This is something you would know from your engineering standouts and readouts. Moving further, we have the larger cylinder, which I know I promised we'd talk about the larger cylinder. We're going to get to all 3 of the cylindrical pieces here shortly. I'll just move on quickly to the conical bow tail at the end of the rocket. So this is basically the same piece as the conical shoulder. It's simply just a flipped, an inverted piece. It's a little bit different sized, of course, but as far as shape goes, which is what determines our normal force expression, it's going to be basically the exact same thing. If we were to take the numbers out of it, we still have a D1 and a D2 essentially being divided by the original conical nose cone D. So for the force here, we're going to have 2 multiplied by this quantity of the squared D values again. The D values here, though, aren't the same as they were in the beginning. The D2 value, of course, is the same because we still have this large cylindrical section that both of the conical portions connect to. Though the difference is this top cylinder may not be the same diameter as this bottom cylinder. In most cases, I think it would be, but for the sake of this problem, we've decided to allow the third cylinder, the bottom cylinder, to be a different diameter. With that in mind, we're going to have 2 times the quantity of D3 over D squared minus D2 over D squared. Again, this would be values you could measure for your rocket, and you would have them in your engineering readouts, and you could calculate this value pretty simply. For the location of the center of pressure on the back portion here, it's actually a very similar process as we found earlier. It's going to be similar all the way through, actually. So x bar sub CB is going to equal xCB plus delta xCB. Again, it's the same process. You can see that we have xCB being measured from the very top of this conical portion to where the force acts itself, and then xCB is measured from the reference line to the top of it. Those two added together gives us the distance from the reference line to the point where the center of pressure resides. So this expression will give us essentially the exact same thing we found in the conical shoulder. Again, just different D values. So here, same expression, except xCB plus LCB, which is the length of this particular portion. So that length could vary from the first conical shoulder portion. This is multiplied by the quantity 1 plus 1 minus D2 over D3, all divided by 1 minus D2 over D3 squared. Pretty much the exact same expression, just different D's again. It should be noted that in the instance that you do have the exact same D3 and D1 values, that the force for the conical bowtail will be the exact same as for the shoulder. The only difference is CB should be negative. So, moving on to the next portion, I told you we would talk about the cylinders. So you can see there are no discussions of cylinders on our board here. There's a specific reason for that. So a cylindrical body, for small angles of attack, so we're talking, alpha less than 10 degrees, the force on any cylindrical body is pretty much negligible, as essentially even further derivations from 90 degrees don't give you that much change in force. Close to 90 degrees, within 10 degrees, you're experiencing a normal force of 1.0, which isn't going to change anything, because if we're multiplying 1.0 into this entire thing, that's not really going to change the scope of much. Which is why all 3 cylindrical bodies do not have to have accounted for forces. They are negligible, therefore we can ignore them. So, getting to the bottom of our rocket, we've got the fins. We know a rocket could have multiple fins all the way around, and I'm sure you were thinking in the beginning when we did our projection, how did that account for the fins that don't get projected, the one we can't see that's on the opposite side, and the one that's protruding out to us that we could see as this line? Well, they get just that. We assumed in the beginning, we had to make the assumption that fins are thin, flat plates. And because of that, their thickness doesn't actually impede motion that much. There would be some drag coefficient forces, but that would be looking at the rocket's flight and thrust. We're looking at the center of pressure. For the center of pressure, these thin, flat plates, while they do have a particular center of pressure, it's not terribly an impedance on the rocket itself and on the movement of the total center of pressure, that is. We do know that generally the rocket's engine compartment is going to be the heaviest portion. So the center of gravity, which is a vastly different thing than the center of pressure, will be further back on the rocket. In a general sense, you want the center of pressure to be behind the center of gravity. So for our rocket, if we could have the center of gravity somewhere within this region, that would be great, because the center of pressure is further back, closer to the engine, and this rocket would fly as it should. So, back to fins. Any fin that isn't overly complex in shape may be simplified into an ideal shape that really only has 4 straight line edges, with the root and the tip being parallel. It's very important when performing these simplifications to be sure that the idealized shape has to be about the same or slightly less area than the actual fin itself. And what I mean by that is, let's say we had a fin that was like this. So fin comes down. So if you don't know, this would be the root, this would be the tip. You would think it's root or tip or root or tip. That's actually not true. So this is the part that's touching the rocket. So here's the root and the tip, kind of like a tree. So when we make this simplification, this has a lot more sides than just 4. You would think, okay, we'll just grab this and make it this entire thing, 4 sides. But what you've done now is you've added in this area. This area is now added. So we had a total area here, and now you've added in a total area here. So the area total would actually be more than the original area that you had. So to correct that, what you would do, let me redraw our shape here. You would take a slanted approach that cuts off a portion of area. So we lose, let me change colors here for a second. So we lose this area, but we gain it here. And we assume that this area and this area are close to one another. That way we're not actually losing any area, we're maintaining the same area totally. For our rocket, the fins are a little bit more simplistic. They are already 4 simple line fins. So we don't have to perform any simplifications on this particular rocket. But looking at the fins, these are generalized, of course. Special cases are going to be handled by a proper use of various dimensions. For example, a triangular fin is going to have values that are different. Rectangular fins are going to have values that are different. We have parallelogrammal fins. So for our fins, they're swept back, essentially. So we have the length of the fin, which is going to be measured from half points on either side. That's the total length of the fin. That's L sub f. Then from a common central point at the tip of the root, I know, kind of counterintuitive to say that, to where the fin slant stops, the first fin slant stops, we have the distance m. The total distance of the left side of the fin, the one that's rooted, connected to the body, is a, and we also denote the half a points. Also on the back end, the tip where it's not connected to the body, we denote that distance b with the half b points. This distance from the root to the tip is known as the span of the fin itself. On this side, you can actually see the span from the root to the tip while it's connected to the body. You also see this r. This r is the radial distance, so the radius between the fins on the body itself. Essentially the radius from the center of the rocket to the root of each fin. And that should be the same all the way around, of course, because our rocket should be circular in shape, the body of it. I don't know if I've seen any rockets that break away from the circular shape too much. So we do calculate the force on the fins pretty much the same that you would for every other component. We've got some xf, that's the distance from the nose tip reference line down to the tip of the root, again, the start of the fins. Then we have some delta xf, which is the difference in distance from that xf point, from the tip of the root, to where the force actually acts on the fins. And then we have the force on the fins itself. Now, interesting note, over here you should notice that our C sub n alpha is denoted FB. And then here, the same diagram, just zoomed in, we have C sub n alpha only denoted F. That is not a mistake, because the fins, each fin has a pressure force. So we have to account for that. And each fin, like I said earlier, is also experiencing some interference based off of its drag and stuff like that. The air that as it flows over the body, where the body connects to the fins, experiences some interference. We're essentially creating a small portion of turbulent flow, and this tries to account for it. So we have to calculate in a fin interference factor. But before we get to that, let's look at what the force is on each particular fin. So the force on each particular fin, we have 4 times the value of n multiplied by s over d squared. D is still that nose diameter from earlier. S is the span length of our fins. This is going to be divided by 1 plus, under the radical, 1 plus the quantity 2L sub f, which is the length of our fins, divided by a plus b squared. Recall that a plus b, or a and b, are the distances from point to point on both the root and the tip. These distances could be the same. These distances can vary depending on what kind of shape that you have. It should be noted that for these kind of calculations, the number of fins must be maintained at 3, 4, or 6. You cannot use 2, you cannot use 1 in this scenario, because of course if you use 0 in this scenario, you would have an improbability the entire force would be 0, as there would be no fins. And you cannot break 6. So when we calculate the interference factor, we get this interference factor K sub FB. This is going to be equal to 1 plus the quantity 1/2 R divided by S plus R. And recall that R is that radial distance between the fins interfering with the body. So the total force on the fins with the interference factor combined is going to be the interference factor multiplied into this original equation for the force on the fins. Then finding the location, same process as earlier, we have to add the XF and the delta XF to get our total X bar sub F. This is going to give us a different expression than we found in the earlier scenarios. So we have XF plus the quantity M multiplied by the quantity A plus 2B divided by 3 times the quantity A plus B. This is added to 1/6 times the quantity of A plus B minus A times B over A plus B. So we can see that this could be a tedious process. You have to make sure you dot your I's and cross your T's, because if you mistakenly put a variable somewhere wrong, it could get easy to mistaken or screw up the problem quite quickly. Luckily, we're not going to take a full actual value here. We're going to look at a generalized scenario, so we're not going to actually calculate anything here. We're going to leave it. If you need to calculate something for rockets, you can. All right, so we can now generalize and combine everything into our total equations. I gotta find my marker. So for the total normal force, which is, if you recall, our C sub n alpha. I'm just going to switch to the black marker to draw them out. We'll just keep the colors up there. So for this particular rocket, C sub n alpha, our normal force, is going to be the nose cone added to the two conical portions, CS and CD, and the fin portion, which we will denote the entire fin portion, so C sub n alpha sub FB. That way we have the fin interference factor already inside. So let's go ahead and take this expression out and add all of our values in that we've taken this far. So we recall for our nose, for most shapes, and this shape in particular, we're going to have 2. For the shoulder, the first conical portion, we came up with the expression that it was going to be 2 times the second diameter over the nose diameter squared minus first diameter over nose diameter squared. Added into the next conical portion, the coming out of the body. Same principle, we had the 2 multiplied by, this time, the third diameter, since we said the third diameter could be different, still over the nose diameter squared, minus the second diameter, the thick portion of our body, over the nose diameter squared. And lastly, the fin portion, which we said was the interference factor, case of FB, times this value for the fin force, which had under, or in the denominator, 1 plus square root of 1 plus 2 times the length of our fins divided by A plus B squared. And then in the numerator we had 4 times N times S divided by D, where S was the span length for the fins and D is still the nose cone diameter. Alright, so let's take this a little further. We can simplify a little more. So we can pull a 2 out of every single expression. So let's go ahead and do that. Let's move over a little bit, actually. Give ourselves a little bit more room. So we pulled our 2 out. So we have d2 over d squared minus d1 over d squared plus these are plus what we have over here, d3 over d squared minus the d2 over d squared. Just making sure to keep your variables there because we have a lot of variables going on. All right, and we're going to go ahead and combine in the kf, or no, actually let's wait on that. We pulled the 2 out of there, so we have k sub fb times 2n s over d squared over 1 plus square root 1 plus 2lf over a plus b, and that value is also squared. Close. And we'll close the entire box. Alright, still some simplification we could do on the normal force. See, I told you it was a tedious expression. So we should see here that we actually have some values that cancel out. So this value cancels with this value, and that's the only ones that cancel out. So we can still take it a little further. So now our C sub n alpha will equal 2, drop the fancy brackets and use normal brackets. Since we can now drop this, we're going to have 1 plus, move things around, so we have d3 over d squared minus d1 over d squared plus, let's go ahead and add in the value for kfb as well, which is going to be 1 plus s plus r under 1/2 and that's times this force value that we should be familiar with writing now, the fin force squared, and all of that is under 2n s over d squared. All right, so that's pretty much the most simplistic expression we're going to get for the normal force for this rocket, which is okay actually. All of these values are now measurable empirical values, and it would be easy to plug in all of the numbers here. So, finalizing, we need to find the location for the center of pressure. So, center of pressure, location. We'll go ahead and mark off our center, or our force expression. All right, so we needed the force expression to actually be able to find the center of pressure. So remember, the total center of pressure is going to be this x bar. And to find that, we needed the inverse of that force value. Inverse is just basically the reciprocated version of this, so all of this under 1. And we'd be multiplying this inverse into an expression that combines the locations for center of pressure for each component, as well as the force value at that particular center of pressure. So starting at the tip, we have the nose, which was Cn alpha sub n times its position, added to the conical portions. And finally, the fin section, which, remember, the force for the fin section has has the interference factor with it as well, whereas the location for that isn't interfered by that. Should also note that particularly for the fins, the location of the center of pressure doesn't actually matter, or doesn't change based off of the number of fins you have. So the value for n for our fins doesn't change the position of the center of pressure on those fins. All it does change is the actual force value itself. All right, so then we can close our box here. So you can see that this expression can get kind of long as well. So if we go ahead and take a look at it, why don't you pause the video and actually try to work this expression out. I will go ahead and wait a minute, and then I'll just put up the final value. So I'm not going to rewrite this out because it's going to be a long expression that we have here anyway. So x bar is going to be inverse, and it's a quite long expression, so bear with me. So Cn alpha for the nose was 2, and the position is 2/3 ln. So we have 4/3 ln. Added to the force on the shoulder, as well as the position for that. So the force was this 2 times d2 over d squared minus d1 over d squared, multiplied by the position, which we found to be xcs plus LCS over 3, multiplied by 1 plus 1 minus the first diameter over the second diameter squared, divided by, or that's that is dividing 1 minus the first diameter over the second diameter. And close parentheses and close the box. Alright, so that was the shoulder, so then we need to add in the boat tail. So adding in the boat tail, we have the force again, pretty much the same value, 2 times, except this time remember d3 over d squared minus d2 over d squared. This is being multiplied by its force value, so its force value was xcb plus lcb over 3, again times 1 plus, and the diameters change once again on us, so we have d2 over d3, d2 over d3 squared, and then 1 minus just d2 over d3. We can close that box. Finally, we can add in the last portion, which is the fins portion. So we had the Cn alpha FB, which if you recall, that was the interference factor multiplied by the original. So let's go ahead and do that. Actually, let's change our front bracket here since we are using brackets a lot. To give a little designation in between where we're at. So, open up first bracket for this guy. Okay, let's see, the interference factor was what? It was 1 plus S plus R under 1/2 R. And that's being multiplied by the original force, which had on the bottom 1 plus square root of 1 plus the length of the fins times 2 divided by A plus B, which are units from the fins, and that was squared. And all of that's dividing for N, where N is the number of fins, S over D, where S is the span length of the fins, and D is still our nose cone diameter. And then that's being multiplied by the position for the center of pressure of the fins, which is also a long expression. So finally, we have XF plus 3 times the quantity A plus B, and this is dividing M times the quantity of A plus 2B, and this is adding A plus B minus quantity AB over A plus B, and that's all being divided by 6, close parentheses. And that, my friends, is our final expression for the center of pressure's location for this rocket in our example. And of course you would need to actually plug in these values. After you've had your readouts checked and your measurements checked, you would plug in these values and get an actual location. But ultimately this would allow you to find the location of center of pressure, and you could also in the meantime calculate the force for that particular rocket, which would be useful in a number of regards, because for one, you're actually going to use it to calculate the center of pressure. So you can see this expression gets even more complex when you're adding in this expression as well. It's a tedious process, but we limited it to algebra. In most cases, calculus will be used, but this is a simplification of that could be used, recalling that we have our given assumptions, and this could be used for any rocket. So it should be noted that going further, any additional shoulders or any other conical pieces or sets of fins must be included as extra terms in the combination equations. So you must include them in basically the force equation here and over here. Conversely, if the rocket does not have certain components, so for instance, if we didn't have these conical components and it is just a cylinder all the way down, we wouldn't have to associate these portion terms. We could simply drop those associated terms to make it more simplistic for a simpler rocket. Well, I hope you have enjoyed, and I hope you stuck with me throughout this tedious process. This is a little basic bit of rocket science, and if you have any experience in algebra, you can say that you can do a little bit of rocket science. Rocket science isn't overtly hard, just a lot of the time it's really, really tedious. So thank you for joining me today, and once again, here is the center of pressure for this basic type of rocket. Happy holidays, New Year's, and well wishes to the next year for you guys.